Welcome to the Ventilator and Pulmonary Mechanics Chalk Talk series, where we're learning how ventilators work and how to work with ventilators. I'm John McManigal. Let's get started. Our last talk and this one are investigating the physiology of hypoventilation and hypoxemia. That's because the next couple of lectures are going to focus more directly on how to work with ventilators. That is, how to increase tidal volume and respiratory rate to treat hypoventilation and hypercarbia, and how to increase inspired oxygen fraction and mean airway pressure to treat hypoxemia. Last time, we derived the alveolar gas equation. Then, we looked at two causes of hypoxemia in the healthy lung: hypoventilation and insufficient inspired oxygen pressure. In this talk, we're going to look at slightly more complicated lung models to explain the remaining causes of hypoxemia: limited diffusion, ventilation-perfusion mismatch, and shunt. Just like last time, you can see descriptions of this physiology in many textbooks and review articles, but I recommend this review by Peterson, an anesthesiologist at the Karolinska Institute in Sweden, and Glennie, a pulmonary intensivist at the University of Washington in Seattle. It was published in the European Respiratory Journal in 2014. So to get started here, let's quickly look back at the two causes of hypoxemia we covered last time. The alveolar gas equation up top tells us that the alveolar partial pressure of oxygen is equal to the inspired oxygen pressure minus the alveolar partial pressure of carbon dioxide divided by the respiratory quotient. Last time, we looked at a simple, single alveolus, single pulmonary capillary lung model with perfect diffusion, meaning that the arterial oxygen partial pressure was exactly equal to the alveolar oxygen partial pressure. And in this model, the two ways that you can wind up with hypoxemia, or low arterial oxygen partial pressure, are first, to have insufficient inspired oxygen, usually due to altitude, but possibly in some odd scuba diving accident due to low FiO2, or second, you can have increased alveolar carbon dioxide partial pressure due to hypoventilation, which will also cause hypoxemia. The reason I bring these causes back up is that there are two questions that are frequently asked about causes of hypoxemia. The first question is there an alveolar arterial oxygen gradient, or is there an AA gradient? Some people prefer to call this an AA difference. But either way, the question is there a difference between the alveolar oxygen and the arterial oxygen partial pressures? That's often written as P big A minus little a O2, and is the difference between the P big A O2, the alveolar oxygen partial pressure, and the P little a O2, the arterial oxygen partial pressure. And we can see by looking at the equation up top, the answer is no. Whether hypoxemia is caused by insufficient inspired oxygen or caused by hypercarbia due to hypoventilation, there is no difference between the alveolar and arterial oxygen partial pressure. I should also say that even a healthy lung is not perfect in terms of ventilation-perfusion matching. We'll see what that means in just a minute, but a normal healthy person does have a small AA gradient. In a young adult non-smoker, that's 5 to 10 millimeters of mercury. It increases by a couple of points per decade of life. So a healthy 40-year-old should have an AA gradient less than about 15 millimeters of mercury. At 60 years old, maybe 20 millimeters of mercury. And at 80 years old, about 25 millimeters of mercury. The next question we ask about causes of hypoxemia is, can you correct the hypoxemia with supplemental oxygen? Or, put another way, if we increase our inspired oxygen fraction, will the arterial partial pressure of oxygen increase significantly? And we can see just from the alveolar gas equation that if your primary problem is a low barometric pressure, a low FiO2, or even a high alveolar carbon dioxide partial pressure causing your alveolar, and therefore arterial, oxygen partial pressure to be low, if you increase your normal room air oxygen fraction of 21% up to 40 or 60 or even 80%, you can very quickly drive this alveolar gas equation in the right direction and correct your hypoxemia. So for both decreased inspired oxygen and hypoventilation, the answer to can you correct it with supplemental oxygen, is yes. As we go along, we'll compare these answers with the answers in each new cause of hypoxemia, namely diffusion insufficiency, ventilation-perfusion mismatch, and shunt. Our next cause of hypoxemia is diffusion insufficiency. Before we look at insufficient diffusion, let's look at the normal diffusion that's happening at the alveolar capillary interface. You have your alveolar partial pressure of oxygen, P big AO2, in the alveolus. Mixed venous blood enters the alveolar capillary with oxygen at a partial pressure of P VO2. While the blood is in the capillary, its oxygen partial pressure is P little CO2. So this is not CO2 like carbon dioxide, it's little c for capillary, O2. And then, in this one alveolus lung model, as the blood emerges from the single alveolar capillary, it is arterial blood, with oxygen partial pressure of P little a O2. So as the capillary blood transits the single pulmonary capillary, its oxygen partial pressure is increasing from the mixed venous oxygen partial pressure, somewhere around 40 millimeters of mercury, to the arterial oxygen partial pressure, which, with perfect diffusion, is about the same as our alveolar oxygen partial pressure. In a normal physiologic state, that would be about 100 millimeters of mercury. So what does this look like in terms of time dynamics? When our capillary blood first enters the capillary, it's coming from mixed venous blood. So it starts with a capillary oxygen partial pressure equal to the mixed venous oxygen tension, here in this blue circle on the left side of the graph. Again, 40 millimeters of mercury is a normal physiologic value. And then the respiratory epithelium is evolved for efficient diffusion. So oxygen diffuses from the alveolar sac through the so-called blood-air barrier made up of a thin layer of surfactant, respiratory epithelium, basal lamina, capillary epithelium, and into the capillary blood very efficiently. And capillary oxygen pressure rises rapidly and hits an asymptote as it becomes fully equilibrated with the partial pressure of oxygen in the alveolar gas. So the remaining question is, what is the arterial oxygen partial pressure? The last variable you need to know is that a normal pulmonary capillary transit time is between 1/4 and 3/4 of a second, and that speed increases as heart rate and cardiac output increase. So our arterial oxygen partial pressure is a nice average of the capillary oxygen partial pressure in this general range of transit time, which is about right. Your arterial oxygen partial pressure is in the high 90s millimeters of mercury. So the green line is capillary partial pressure of oxygen, and the red line represents arterial oxygen partial pressure. You can probably already pick out some of the situations in which insufficient diffusion would result in a lower arterial oxygen partial pressure. They are a limitation to the diffusion itself and a rapid transit through the pulmonary capillary. So the graphs I've laid out here are exactly the same as above, with a dotted green line representing normal diffusion, just like we drew a minute ago. So the alveolar partial pressure of oxygen is in yellow, mixed venous oxygen partial pressure is the blue circle, and normal capillary oxygen partial pressure is in the green dotted line. We'll look at diffusion limitation first. You see this classically in interstitial lung disease, pulmonary fibrosis, for example. The respiratory epithelium becomes harder for oxygen to diffuse through, so diffusion becomes slower. You'll still start at mixed venous oxygen partial pressure, and you'll still have your asymptote at alveolar oxygen partial pressure, but the diffusion speed will be much slower. So now, when you look at a normal transit time across that capillary, being between 1/4 and 3/4 of a second, your arterial oxygen partial pressure is going to be much lower than it should be. It should be up here somewhere almost at 100 millimeters of mercury, but instead you're hovering down here around 80 millimeters of mercury. Contrast that with a rapid transit situation. In this case, there's nothing wrong with the respiratory epithelium, so your capillary oxygen partial pressure over time is going to be the same. But if you really get your heart rate up and your cardiac output high enough, instead of your normal transit time of 1/4 to 3/4 of a second, instead you have a somewhat shorter transit time, so your arterial oxygen partial pressure is decreased. And this requires such a high cardiac output that it's really only attainable by Olympic-level athletes. Now, in reality, what you can sometimes see is a mixture of these two pathologies. Here's your patient with moderate to severe pulmonary fibrosis, and in general, their capillary transit time is normal in this 1/4 to 3/4 of a second range. And they're doing all right. Their normal arterial oxygen partial pressure is in the high 80s or low 90s. But when this patient gets up to walk, increases their heart rate and cardiac output, not to Olympic levels, but just a modest increase, that then decreases their capillary transit time just enough to dip their arterial oxygen partial pressure down to the low 80s or 70s. So this is your typical pulmonary fibrosis patient who's kind of hanging in there at baseline, but as soon as they do any kind of activity, they need supplemental oxygen. So to wrap up diffusion limitation, let's go back to those two questions that we're asking about every cause of hypoxemia. First, is there an AA gradient? Is there a difference between the alveolar oxygen partial pressure and the arterial oxygen partial pressure? And I think it should be pretty clear here that the answer is yes. And number two, can you correct the hypoxemia with supplemental oxygen? And hopefully it's not too hard to see here why the answer again is yes. Your alveolar oxygen partial pressure on room air is only around 100 millimeters of mercury. But if you gave this patient supplemental oxygen, you can increase their alveolar oxygen quite high. And that action in and of itself will drive the capillary oxygen partial pressure curve up because diffusion speed is proportional to the difference, the gradient, between alveolar and capillary oxygen partial pressures. So now, even with the same transit time, your new arterial oxygen partial pressure is significantly higher. So the answer to does supplemental oxygen correct the hypoxemia is yes. Next, we have the most common, which I'm afraid is also the most complex reason for hypoxemia, ventilation-perfusion mismatch, generally abbreviated as VQ mismatch. In order to explain this one, we're going to have to move from our one-compartment lung model to this two-compartment lung model. Your pulmonary artery is now splitting into two pulmonary capillaries, each with equal blood flow. Each of these capillaries diffuses perfectly with its own alveolus, and then the end capillary blood from each, which is indicated by this C', recombines into our arterial blood. Now, what makes this model interesting and gives us the VQ mismatch that we're talking about is that even though these two lung segments are perfused equally with blood, their share of ventilation is quite different. We can draw little bumps in this bronchiole to represent ventilatory obstruction. You and I sitting here have this to some degree. Gravity causes a difference in blood flow and ventilation to different areas of the lung in a healthy person, which is what causes the quote-unquote normal AA gradient. But VQ mismatch is dramatically increased in many disease states, especially obstructive lung diseases like COPD and active asthma. Emphysema would be your classic example. The way that we measure the relative amount of ventilation and perfusion in any segment is with the ventilation-perfusion or VQ ratio. So a normal matched lung segment has a VQ ratio of 1. In a normal healthy person, all of your lung segments range in VQ ratio from 0.3 up to 2 or so. If you had an area of lung that's perfused by blood, but there's no gas ventilating it, that is a VQ ratio of 0. If you have a lung segment that's getting gas in and out, but doesn't have any blood flow to it, that would be a VQ ratio of infinity. What makes figuring out what's going on here a little bit trickier is that your alveolar gas partial pressures in segments with different VQ ratios are not equal, and they're not very easily calculated. There is no simple equation for this stuff, but we can start to get an idea intuitively of what this relationship looks like. On this graph, we'll look at the alveolar partial pressure of oxygen and carbon dioxide in a lung segment on the vertical axis, compared to the VQ ratio of that lung segment on the horizontal axis. we'll draw oxygen in red and carbon dioxide in blue. It should make sense that if your VQ ratio is 0, that is, you have no ventilation going into the alveolus, then your alveolar gas partial pressures will be equal to your mixed venous partial pressures. And a normal mixed venous carbon dioxide partial pressure is right around 45 millimeters of mercury, and a normal mixed venous oxygen partial pressure is right around 40 millimeters of mercury. It should also make sense that if your VQ ratio is exactly 1, that's normal alveolar gas exchange, governed by our old friend the alveolar gas equation. So in that case, the carbon dioxide partial pressure is right at 40 millimeters of mercury, and the oxygen partial pressure is 100 millimeters of mercury. Then, as your VQ ratio goes to infinity, that is, a lung segment that's very well ventilated, but has practically no exposure to mixed venous blood, you'll wind up with a situation where the alveolar gas partial pressures will just be the partial pressures of the breathing gas. The partial pressure of carbon dioxide will be about 0, and the partial pressure of oxygen will just be your inspired oxygen pressure, which for sea level room air is 150 millimeters of mercury. And unfortunately, you need computer models to connect the dots between these curves. There's no easy formula for it, but it winds up being right about here for oxygen, and it's down around here for carbon dioxide. So that's at least a bird's eye view of where the alveolar oxygen and carbon dioxide partial pressures come from in these two alveoli in our model. The alveolus with a VQ ratio of 2 has an oxygen partial pressure of 118 millimeters of mercury and a carbon dioxide partial pressure of 35 millimeters of mercury, and the alveolus with a VQ ratio of 0.1 has both oxygen and carbon dioxide partial pressures right around 45 millimeters of mercury. And in this model, we're going to go ahead and again assume no diffusion limitation. So your end capillary oxygen and carbon dioxide partial pressures are exactly equal to the alveolar partial pressures. So the question that remains is, what are your arterial oxygen and carbon dioxide partial pressures after these capillaries mix? To answer that question, we need to look at the content of each gas contained in the capillary blood. So one more time, with no diffusion limitation, in capillary 1 on the left, the carbon dioxide partial pressure is 35 millimeters of mercury, and the oxygen partial pressure is 118 millimeters of mercury. In capillary 2 on the right, the carbon dioxide partial pressure is 45 millimeters of mercury, and the oxygen partial pressure is also 45 millimeters of mercury. So you probably remember we can't necessarily just average the partial pressure numbers because the resulting arterial gas pressures depend on mixing the content of these gases in the blood. So if we start with carbon dioxide, the content of CO2 in the blood is straightforward diffusion by mass effect into the blood at a solubility of 0.06 milliliters of CO2 gas in every deciliter of blood for every millimeter of mercury of CO2 partial pressure. So that means that capillary 1 contains 2.1 milliliters of CO2 per deciliter of blood, and in capillary 2, that's 2.7 milliliters per deciliter. When these two capillaries recombine, you can take the average carbon dioxide content of 2.4 milliliters per deciliter, and then running the diffusion equation in reverse, you find that the arterial partial pressure of CO2 is 40 millimeters of mercury. It becomes a little more complicated when we turn to oxygen, because we have hemoglobin carrying most of the oxygen in our blood. So an oxygen partial pressure of 118 millimeters of mercury corresponds to 100% saturated hemoglobin and an oxygen content of 20.5 milliliters of oxygen per deciliters of blood, assuming a normal hemoglobin content. An oxygen partial pressure of 45 corresponds, if you look at a hemoglobin saturation curve, with a saturation of about 75% and an oxygen content of 15.2 milliliters per deciliter. If we average the oxygen content in these two capillaries, we find an arterial oxygen content of 17.85 milliliters per deciliter, That works out to about an 88% hemoglobin saturation and an arterial oxygen partial pressure right around 70 millimeters of mercury. So if you actually ran an arterial blood gas on this patient, you would find a PaCO2 of 40 millimeters of mercury and a PaO2 of 70 millimeters of mercury, and your pulse oximeter would be beeping along at 88%. And the entire reason for the hypoxemia is ventilation-perfusion mismatch. Let's ask our two standard questions. First, is there an AA gradient? Well, with two different alveoli with two different oxygen partial pressures, how do we compare alveolar and arterial oxygen pressure? The answer, by convention, is that we calculate the ideal alveolar partial pressure of oxygen using the alveolar gas equation. So alveolar oxygen partial pressure equals inspired oxygen pressure minus alveolar carbon dioxide partial pressure divided by the respiratory quotient. And to get this ideal value, we substitute the measured arterial carbon dioxide partial pressure in place of the alveolar carbon dioxide partial pressure. So this equation gives us an ideal or expected alveolar oxygen partial pressure, and if you run it with our measured arterial carbon dioxide tension of 40 millimeters of mercury, the sea-level room air PiO2 of 150 millimeters of mercury, and a normal respiratory quotient of 0.8, the ideal alveolar oxygen partial pressure works out to be 100 millimeters of mercury. And of course, that's what you would expect in a situation with a VQ ratio of 1. So now the question, is there an AA gradient, can be answered. Our AA gradient is 100 minus 70, which is 30 millimeters of mercury. So the answer is yes, there is an AA gradient in hypoxemia due to ventilation-perfusion mismatch. And the second question is, can you correct the hypoxemia with supplemental oxygen? To answer that, let's go back up to the graph that gave us the partial pressure of oxygen in each of our pulmonary segments. If we suddenly increase our inspired oxygen fraction to about 40%, our graph is now going to look something like this. And even a segment with a VQ ratio of 0.1 will have a very healthy alveolar oxygen partial pressure. So the hypoxemia of VQ mismatch will correct with supplemental oxygen. So our answer to question number 2 is yes. One last thing I want to point out before we change gears from ventilation-perfusion mismatch is that this VQ mismatch is the reason that when using a ventilator, you increase your mean airway pressure, generally by using positive end expiratory pressure, or PEEP, to improve oxygenation. When you increase mean airway pressure, you can pop open some of these obstructions, decrease atelectasis, and recruit lung volume, and all of those effects have a net result of decreasing the number of segments in your lung with a low ventilation-perfusion ratio and improving VQ matching. That wraps up ventilation-perfusion mismatch and leads us to our final cause of hypoxemia, shunt. Shunt is really just a special case of ventilation-perfusion mismatch. We're still going to use the same two-compartment lung model here, and we're not going to repeat all of the equations we just went through. Instead, we'll just point out the differences. In shunt, you assume that one of your lung segments has absolutely no ventilation despite having perfusion. Of course, throughout your lungs, the pulmonary arterioles will constrict in the presence of hypoxia, which works to reduce VQ mismatch generally and shunt specifically. But shunt arises when that hypoxic vasoconstriction reflex is insufficient or overwhelmed. For this model to be realistic, you'll have less blood going through the shunt pathway compared to through the capillary of the aerated alveolus. Your standard example of shunt is an alveolus completely full of fluid, like in bronchial pneumonia or ARDS. You could also have no ventilation because of a bronchial tree obstruction, like a foreign body or a tumor, or you could have mixed venous blood bypassing the capillary circulation entirely due to an arteriovenous malformation or a congenital heart defect with Eisenmenger physiology. So how does shunt compare to the more general VQ mismatch we just looked at? The truth is, the effect on arterial oxygen partial pressure is the same. When mixed venous blood proceeds directly into the pulmonary vein without exposure to alveolar gas and mixes with systemic arterial blood, it decreases the arterial oxygen tension. Just like the VQ mismatch we looked at, this does also increase the arterial carbon dioxide partial pressure a little bit, but the effect of hemoglobin as an oxygen-carrying molecule makes the decrease in oxygen partial pressure much more pronounced. So let's go ahead and answer our two big questions about causes of hypoxemia. First, is there an alveolar arterial oxygen gradient? For exactly the same reasons as we already discussed with VQ mismatch, the answer is yes. The alveolar and arterial partial pressures of oxygen are different, so there is an AA gradient. Now, can you correct the hypoxemia of shunt with supplemental oxygen? Here, we have the difference between true shunt and VQ mismatch. Remember, in VQ mismatch, the reason that increasing inspired oxygen fraction improved hypoxemia is because it increases the alveolar oxygen partial pressure in low VQ segments. On this graph of partial pressure versus VQ ratio, that's represented by the red curve increasing much more rapidly. But in true shunt, the blood flowing through the shunt is never exposed to alveolar gas at all. We're stuck here at 0 on the horizontal axis of this graph. And so no matter how much oxygen is in our breathing gas, the capillary won't see it. Deoxygenated venous blood is mixing directly with your arterial supply. So no, supplemental oxygen will not correct the hypoxemia of shunt. Okay, in summary, we looked at the 5 mechanisms of hypoxemia: hypoventilation, insufficient inspired oxygen, diffusion limitation, ventilation-perfusion mismatch, and shunt. For each, we examined whether there's an elevated alveolar arterial oxygen partial pressure gradient. For each, we looked at whether increasing the inspired oxygen fraction can correct the hypoxemia. And for each one, we looked at a classic clinical example. Finally, we learned that the reason we increase mean airway pressure, usually by increasing the positive end expiratory pressure, in order to improve oxygenation, is that by adding more airway pressure, you decrease atelectasis, recruit more lung segments, thereby decreasing ventilation-perfusion mismatch. Next time, we're really going to get into how to work the ventilator. We'll use what we've learned in these last couple of lectures to dive into how to correct hypercarbia and hypoxemia by adjusting ventilator settings. Thank you so much for your attention. I'll see you next time.